Great to see everybody. Let's go ahead and start with this. And good to see everybody after, let's see, I was out last week, so hopefully you had a good weekend, enjoyed a little bit. Hopefully you're ready for a little bit of a break here too as Thanksgiving arrives. So make sure to enjoy that fully, whether you're going home or I think there's usually festivities and like a campus dinner and those kind of things, so keep an eye out. At least in years past, I remember that being true. Does anybody actually know? Usually in like the across from Rock. Okay, yeah. Yeah, take advantage if there's a big free feast. I think at least in the past, what is it, the International Village across the street? Yeah, is that the one? Usually they have something. But anyways, with that said, today we might end a little bit early today. There's a little bit of activity, and can have some time to chat with folks about final projects too. But I want to talk a little bit about some data structures today in C++. Maybe this will come helpful for your final project to talk about graphs a little bit. And just to warm us up, there's a really nice C++ library, or at least to reference and sort of know what's available. It's called the Boost Graph Library. I've mentioned Boost a few times. I think it's going to be one of our sort of auxiliary topics at the end of the semester, showing you how to work with it or install it, or kind of just working with some code that's available in C++. But anyways, they've got a graph library, so if you've heard of any of these algorithms, quite likely you'll see most of these in your algorithms course. Things like Dijkstra's shortest path. Again, maybe some of you folks have seen this. Well, it's built into a library for you, which is kind of nice. Nice to have these sort of tools available that you can choose out. So just wanted to make that available to you. And again, it might be useful just to sort of skim because it's relevant to the topic that we're working on today. And give you a bonus warm-up too. So again, the reason I was out at a conference, Handmade Seattle. Did anybody by chance watch or click on the link? Or they were streaming it live on Twitch, so you might have seen me speaking live. They very formally introduced me as Professor Mike and said, wow, we have a professor here speaking. They were very happy. But anyway, the topic, why I'm mentioning this again, is it's relevant to this class. I was talking about memory allocation. So a lot of the stuff that you folks learned about, but also building your own version of new delete, these types of things, so memory allocator. So that's something, maybe you might also be interested in, if you're more interested in the systems side of the course. I'm very much a systems person, taking a look at this, and that could be a final project. So just wanted to throw that out there. It was also just a fun conference. And the good news is they're coming to Boston next year. So it's going to be Handmade Boston. So I think that's relevant to all of you folks. Whether you'll want to volunteer there or whatever. So lots of cool stuff going on there, and not just C++ stuff as well. Let's see, what else to say? Course logistics, go to the calendar in a moment, but as you know, the final project's out, so I looked at all of your, from last week, the in-class activities for your project ideas. I think most sounded pretty good, so unless you got an email from me saying, hey, this sounds a little bit wild, or we might want to, change the scope. You should be good to go and go ahead and begin. I think there might be one or two I might want to take a closer look at. I think somebody was trying to do something with, I won't say what it was, but it sounded very ambitious. So go for it, but just make sure you have a scope that you can achieve. So that's for the final project. And there will be one more assignment that comes out probably tomorrow at some point. It's going to be on something related to graphs, and that'll be the final assignment. And then we'll have a week or so to work on that. Not counting break. Break will be break, and then the rest of the time for your final project. So we're wrapping up pretty soon. Which is, goes by pretty quick, I guess, especially after Thanksgiving. The semester is basically over at that point. But there are some other exciting announcements, and I'll remind folks again of this. We are going to have another guest speaker. It's going to be virtual. Did folks see the talk announcement come out? I don't know. I guess you get a million of them probably too. But I'll be sure to remind you, December 5th. I might make this class optional, whatever the topic is. I need to think about it if you attend the talk, or vice versa. The speaker's name's Victor Sierra. He's working at Microsoft right now. He's a senior engineer there, and he's been doing really cool C++ stuff for like 20 plus years. And he lectures at his alma mater frequently, so he's a very good talker. And you're definitely going to learn something. It's going to be about performance and linked lists and these types of things. So I think that should be a lot of fun. I'm looking forward to it. That's why I was happy he agreed to speak. I think it'll be a treat for you folks too. So that's what's coming up. And then again, no class Wednesday. I think somebody had told me it's technically like half a day or something. I think there's no class Wednesday as we looked on the calendar, but yeah, we won't have class. Let's see. All right. With that said, any questions about what's going on in the class, course logistics, anything? All right. If not, let's go ahead and dive into our topic today, which will be talking about graphs. So let's go ahead and see what these are all about. But before we do that, so last lecture threw a few topics out at you. Originally, it was going to be a review, but kind of some more relevant things, some language-specific things I talked about were functors and lambdas. So I ended up just throwing out two of the YouTube videos I had on those. But so functors, function objects, really important tool in things like functional programming for holding state, but also showing you how to build a class and overload that parens operator. Okay, so it's basically can use objects like function calls, and those often come in handy when passing into another function some behavior. Okay, so I think from the video I showed an example of using functors for sort. I might have done, I think was the example, and sort of doing different comparison. So that was functors. Kind of a funny name thing, stands for function objects. But were folks able to watch that video? Yeah, I see head shakes. That's what the in-class activity. Did you watch this? Yes. So hopefully you were able to watch that because they are directly related to the next topic, lambdas, which I think a lot of folks these days who are teaching C++ kind of introduce lambdas, but you don't realize it's actually just a functor in disguise. So that's kind of neat, again, in my opinion, important, I think, as you go forward in C++, just to understand how these different constructs are implemented. So lambda is basically just a unnamed functor. But behind the scenes, again, if you go on CPP Insights, you'll see that a lambda is just a function object that's created for you. And depending on how you create that lambda, things will be read-only or mutable and so on. Okay, so that was the idea. And then part of that lecture, again, sort of optional, maybe for folks who are preparing more so for, careers in C++ or thinking about that actively as you're applying for internships and co-op. I just kind of put some of the standard questions that I've gotten on C++ at the end of that slideshow. So those could be things that you think about, look at. Most of those things we've covered in this class. Some things we haven't. So that might be a good thing for you to look at as well. And of course, there was the C++ Jeopardy. So depending on how much fun you had playing that, you could pause and sort of test yourself. Again, some things we've talked about, some we haven't. Hopefully gives you pretty wide coverage of C++. All right. And I think there was even some stuff at the end about quad tree or whatever, and compilation. So just some interesting things to have all in one place. All right, but with that said, what I want to go ahead and talk about now, if there's no questions, is graphs. Okay, and we've already talked about one type of graph in this class, at least one. Specifically, I'm thinking about binary tree, which we've done a homework on, which is a tree is a graph. It's a acyclic graph, so a graph without cycles. Okay, but the difference is today we're going to talk more about just generic graphs, nodes and edges that are connected. Okay, so I'll try to define those a little bit more rigorously here. Okay, so the sort of bad news, I guess, is there's no built-in graph data type in C++. The good news is they're relatively simple to make. We just have to choose the representation. Or, as I mentioned in the warm-up, we have things like the Boost graphics library, which can help us with lots of common tasks that we might want to do, navigating graphs, traversing them, finding shortest paths, all these different things. All right? But let's start from the basics. What a graph is, again, might be a review for those of you who've looked at this more or less in depth and discrete. But as far as graphs are concerned, we have nodes and edges, just like trees. So here's an example. B is a node, and then we have an edge connected from E to D or D to E here. Depending on the field you're working in, you'll think about these as maybe nodes and edges, as I've listed here, or sometimes vertices or a vertex. So I'll kind of use those terms interchangeably. In computer graphics, again, I'm thinking of things in terms of geometry. So oftentimes I might say vertex here. That's the same thing as a node. If you're coming from more of a visualization, more of a data science background, you might think about these as links instead of edges, but it's all the same thing. Okay, so whatever domain you're in might change a little bit here. So more formally, what you're going to see this represented as a graph labeled like this, which is the set of vertices that you have and the set of edges. So you'll usually see this is the most compact mathematical form here. So graph G consists of vertices V and edges V here. Okay, and as we talked about, your set of vertices and your set of unique edges. Okay, and then again, an edge is just a line segment between two nodes. Okay. Other math notation, again, the bars along each side, that's the length or the size of that set. Okay. All right, so a little bit of review there. Now, why graphs are sort of interesting, to study in computer science, why you start looking at them as early as, discrete math or your first, maybe even fundies a little bit, is that they're basically our way to model data and relationships in computer science. So the kind of trick is, if you want to take any problem that exists in the world, is you try to say, hey, how can I represent this as a graph? What are my nodes? And then what's the relationship between two nodes or two entities? And those are your edges or links between them. So, that's sort of the secret too. I guess if you get a interview or something, and it's one of these very generic questions, you kind of try to figure out, how do I transform this problem into a graph? Okay. So here's just some examples of those. Right. So if you think about Google Maps, which would, again, a map would maybe be an obvious application of a graph, right? Your nodes are maybe your street intersections, and the edges are the highways or the roads in between them. When it comes to other things, social media, right? Twitter is a great example to use. There's all sorts of stuff going on. Your people are your nodes, and are they following somebody else, or connected, or friends? That's the sort of relationship. Okay, so just some examples here of where graphs are used or how you might think about this. Okay, so more specifically here again, social networks. Again, take your pick. Twitter's pretty popular these days, or Mastodon. Has anyone made the migration? Maybe for folks following the drama, okay. The Elon Musk takeover and so on. All right. So that would sort of be a distributed graph. Again, maybe you could have multiple graphs, right? They don't all have to be connected either. Something I don't have here. This is a forest over here, and you could have another forest that's not connected. All right. For my computational biology folks, I know I've got a handful. Common use case is protein-protein networks or protein-protein interactions, trying to figure out which individual proteins have some sort of relationship or activate or maybe are a catalyst for something else. So you can kind of traverse these networks here. All right, let's see. The World Wide Web, another kind of obvious one, but hyperlinks are connections. Right, so if you're trying to build a web crawler and you started from my site, well, I have here, what are the links I have? Well, Northeastern links to my page. So maybe you'd start here, but kind of just look and kind of scrape and find, anywhere there's href and say that's okay, relationship here. And then, for my website, you can get to Nick's House of Pizza. And I don't think they link back to mine, so this isn't totally true. But that's the idea here for building a little web crawler. And then one of the two things, or one, not both, the things we'll look at in our homework. So two sort of interesting use cases. Node link diagrams at the top right here. And these are used pretty often in more creative tools, so Photoshop, games and stuff. Or maybe you've done some programming where you're sort of just dropping entities and kind of linking them up to something else, and this sort of forms a path that's doing something. Now here it's showing how if I connect this image to some other node that maybe spins something, then you get that as an output. And that's what's known as a node link diagram. So that's another type of graph. Okay, it's very directional. It's sort of the input to the next output to the next output. Other neat things you can do in graphs, you see these more so in movies. If you have somebody's face here and you're trying to identify different features, so this is getting a little bit into computer vision stuff, and then features of another object. Well, if you can form a relationship between them, in this case a one-to-one mapping, maybe just look at the eyes here of this person, and then this, I guess this would be a jaguar. Well, you can kind of see how you can transform one image to the other, and that's kind of cool. So you've probably seen that effect in various movies, whether 2D or 3D. The first Lord of the Rings sort of has a famous transformation like this. That was state-of-the-art back then. But anyway, these are just graph problems, different ways that you can use graphs. So we're going to do one of these two for the homework. I just haven't finalized, I guess. All right, so anyway, the takeaway with graphs is, think about any problem that you're trying to solve and try to transform it into a graph. I think that's just a good exercise, and once you can do that, you get an access to, all of computer science, right? all the years of graph algorithms and things that folks have figured out. All right, so just a few more things with, graphs, the different types. This is, so once you've sort of figured out, hey, what are my nodes, what are my edges, we still have yet to figure out a few other relationships between those things. Meaning, do we have a directed or an undirected graph? So again, think about the Google Maps example. Is it a one-way road or is it two-way? Can I travel in both directions? And usually we don't put the arrows here, just a line. Or can I only go one way? So we've got a link just in one direction. So again, that's sort of a property of our graph that we have to think about. And then we think about, is it a weighted or an unweighted graph? So again, that's on the edges. What's the sort of weight here? And maybe, again, if this is a map, these weights represent distance, if that makes sense. Sometimes we also break this into a third category of it being negative weighted, so can these values be positive or negative? In the case of an actual map, right, for covering distance, always positive. But there might be reasons to have negative for monitoring some type of flow of some type. All right, so those are a few different types of graphs here. Again, more categorizations thinking about connected versus unconnected. Again, something common to think about in a social graph like Facebook. Do you have any connections? With Mark Zuckerberg, right? You would be on the same sort of graph here. So that's something you could be thinking about. For this class, we're just going to think about connected graphs, but no reason we couldn't otherwise have an unconnected graph. Let's see. And then oftentimes, here's a few, this is an unconnected graph. We've got a few components that aren't together. But oftentimes we will just refer to these as connected components. Okay, that's a property. We'd have to sort of search or traverse each of these graphs here, all of our vertices, and see if they're connected with something else. Okay, so oftentimes we like to, figure out if I'm, and again, maybe the way to think about this again is geography. Maybe this is Australia or something up here with 4 connected cities. This is North America, and this is New Zealand or something, different island. And thinking about, can I get from this place to this place by driving? Okay, well, if we're not connected, we cannot. We have to take a boat or a plane or swim or something. All right. So other interesting properties. Again, just giving you the full summary on graphs. Let's just sort of think about if our graph is dense or if it's sparse. And usually that's measuring just how connected are our nodes here. So usually we'd kind of look at every node here, A, B, C, D, E, F, G, and try to figure out, what does dense mean? Is it highly connected? So usually we're looking at each of these nodes and then maybe the out degree or the in degree, and kind of using that as sort of a measurement of, well, this is a very dense types of graph here. Okay, versus this one, which is a little bit more sparse. Okay, so maybe this one is, us in this class, our friendships, we know each other, right? Everybody sort of knows each other, very close-knit group, versus this is, a bunch of, strangers getting lunch or something. So more or less sparse. Now, why might folks think that this is an interesting property to measure, the density or sparseness of a graph? What do folks think? It's going to kind of lead into our next topic, I guess. And we could give sort of any example, I guess. It's probably something you think about, or will have to think about, certainly when programming. It actually has to do with just our representation of this actual data structure. Do we want it to be, if we're going to have a very dense graph, our choice of data structure is going to matter for how fast maybe we want to either traverse this graph or look at the connections, versus, if we have something more sparse where we have about as many nodes as edges, maybe we can use some other data structure that'll be more efficient. Okay, so it kind of helps us model our problems if we think about things in terms of the density or the sparseness. So a lot of data structures, as you go more into advanced algorithms, courses actually on algorithms, again, you might think about this property. And oftentimes, that's sort of the next step you can think about. Even if you don't see it in 5800 or 3000 algorithms courses, you'd say, okay, what are specific instances of some data structure where it's dense or sparse? Alrighty. All right, so that kind of leads us into the next slide here, which are data structures to support graphs. So again, how do I represent things? And again, that's speaking directly to, do I have a very dense graph or a sparse graph? All right. So we've got two sort of key actors here, or two data structures that I'll introduce. Again, there are many. If you come to take computer graphics, we'll learn about a few more as well. Again, if you're graphically modeling a 3D shape, then again, it's basically some sort of collection of vertices and edges. But here's two pretty good data structures that will cover most of the things that we'll need. The first is called an adjacency matrix. The second is called an adjacency list. And when I'm talking about adjacent, again, that means next to or connected to. Okay? So you can kind of think about a matrix as the mathematical sort of two-dimensional array, and then a list, just like linked lists that we've been learning about, but are keeping track of which node is connected to other edges. Okay, that's the idea. And both of these representations work fine whether you're working with any of the types of graphs we looked at. A directed graph that's connected in one link, undirected if we want weights, or if it's unweighted. Okay, or if it's got negative weights. Anything will work fine. Okay. All right, so let's take a look at the first one. So I'll show both of them, and then we'll take a break, and then I'll show you the actual code for how you might represent one. But the first one is adjacency matrix. Again, it's just like a matrix like you might use in math. How many folks have done like a 2x2 or 3x3 matrix multiplication, or maybe you had to calculate the determinant of a matrix at some point in your school? Yeah, so that was the idea. But we're doing the same thing here, except I'm representing the matrix. This one's 8 by 8. So 8 rows going across, 8 columns going up and down here. It's a little bit bigger, but this tends to be, again, how we can represent a graph. Okay, now why is this 8 by 8? Well, you can kind of see the rows and the columns are the vertices, and they match up here. So 1, 2, 3, 4, 5, 6, 7, 8. And each of those, again, maps to, whatever row or column this vertex is. So let's go ahead and just kind of look at one of these, actually. So if I look at 1 here, vertex 1, and I can kind of go up to row 1 that's going across. Actually, here's one I can actually reach here, sorry. Let's look at 5. So I have 5 here. And then I can kind of see, well, if I go across this row here, the columns where there's a 1, that's something I'm connected to. So 5, let's see, am I connected to 1? No, am I connected to 2? Yes, I am, 1 here. So 5, and that's just stating, hey, I can get to 2, and it takes me, 1 is the distance here, okay? By default, if you don't see 1s or the weights on each of the edges, that usually means 1. That's what's implied, okay? So that's the idea. That's how we read this. And again, I don't see arrows going in any direction. So if I look at 2, I should see a 1 here by 5. So if I go to row 2, scroll over, oh, yep, there's a 1 there. So we are connected. Okay. So that's what this data structure is telling me. My connections. Okay, who am I adjacent to? Which nodes? Okay. And in the positions, if it's 0, I'm not connected. If it's anything else, then I am connected. Okay, if you see negative values, we're still connected, but it's just a negative weight for whatever that means in the problem you're solving. Does that make sense for folks? Okay, awesome. Have folks seen this previously? Some folks have. Some folks, most folks are not in the head. All right, awesome. All right, we'll get to coding it then shortly here. All right, so again, as I mentioned, just again in words here. All right, so it's kind of a nice data structure, I guess. I'll contrast it with the other one, but it becomes really quick for us to just, you could imagine representing this as a array, right? We've worked with 2D arrays plenty in this class. It's 8 by 8 with integer values here, and then you just check. At index, 5 in the row, perhaps. So we sort of select our row here, and let's assume it's 0 base. So if I say index 5, it puts us at 4. Index 0, am I connected to this first node? I am not. Okay, so we can quickly query, in O of one time, just one call lookup if we're connected. Okay. All right, so that's adjacency matrix. And from this data structure, again, we can query, like I said, if we're connected. We can also gather some other nice properties as well, such as how many nodes are coming in. So for example, for 5, I've got 1, 2, 3, 4 connections coming in. And in this case, I've also got 4 connections coming out. 1, 2, 3, 4, since it's bidirectional here. But we can figure that out quickly by just reading from 5 across here what the actual degree is, okay, at that node. Okay. And I have an example here. Okay, so you can quickly see that for this particular node here. Okay, so depending on your representation, you can read sort of across the rows. That might be your in or your out degree. Let's see. Okay, what else do we got here? Here's just in degree versus out degree. So how many nodes are coming in versus out? All right. All right. So adjacency matrices or adjacency matrix, great data structure. Again, if we know exactly how many nodes we're going to have, because then we don't have to resize it, right? If it's always going to be 8 by 8, for instance, that's great. But sometimes we don't, right? So when we have to resize things, then oftentimes we have to think about either another sort of dynamically sizing data structure. Okay. And I'll actually show you today a adjacency matrix you can resize relatively easy, but generally speaking, another data structure that we use is adjacency list. Okay, lists are generally easy to expand, but what does this look like? Have folks seen this data structure before, adjacency list? I got half nods mostly, so I'll keep going at the pace I'm going. Relatively quick here. But basically an adjacency list is an array of lists. So again, going down here, 1, 2, 3, 4, 5, 6, 7, 8, all the items here on the left-hand side in yellow. And then the things that are contained in my list are my connections. So 8 here is connected to 3 and 7. Right? They're traversing this list here. So from 8, let's find it here. I am in fact connected to 3 and 7 here. Okay. Now, immediately here, can anyone tell me a little trade-off between adjacency list versus adjacency matrix? Which one's going to be faster if I just want to say, is 8 connected to 7? Adjacency list or adjacency matrix?
The matrix.
The matrix, right? Yeah, because this one we had to traverse. Yeah. Yep. Exactly, yeah. Worst case, we have to check every single node to see if we're connected here. All right. All right. So there's our nodes. Here's our list. And then, since we have to check everything that could cost us O of n versus the matrix, which was O of 1. But here's another question for folks. So getting to this time thinking about the space. If we have v nodes and e edges, so again just our graph, then how much memory do we need in terms of big O for this representation, or adjacency list? Yeah.
V plus E.
Yeah, v plus e, the number of vertices plus the number of edges. Okay. Now how much would we have needed for our adjacency matrix? Yeah.
V squared.
V squared, yeah. So regardless of how many connections we have, we're always 8 by 8. So if it's very, very sparse, maybe this is a better representation, right? V plus E. So you can imagine, again, just to bring this back to our examples, Facebook, I don't know exactly how many users they have, but it's over 1 billion, right? So you can imagine them maybe saying, well, do we want a 1 billion by 1 billion matrix, whatever that number that multiplies out to. Think about how many connections you have. And most of us, even if we're very popular, right, it's probably in the thousands, maybe, right? No, maybe some of you are in the millions here, I don't know. But, so that's something, again, you have to really think about when you have big data. And Facebook's not even a great example. Probably the even better ones are those protein networks that can be either very sparse or very dense. So again, you have to think about, these are the trade-offs that we're making here. All right, and there's our answers. All right, so just kind of summarizing these again. It's really about, do we need random access so that we can quickly access something, and we're going to trade space for that, so using a lot of memory, or do we want something that's a little bit more sparse and memory efficient, but it might cost us more if we're going to constantly sort of query if something's connected, okay? Because that'll be one of the things that you often sort of have to think about. Are we connected through this route? And what I mean by that is, well, I guess it's sort of a question or something to think about. If you were Google Maps, what would you do? Would you build a adjacency list or adjacency matrix? What would you be thinking about, I guess? Or would you use both and maybe like subsets of each strategy? It's something maybe to think about a little bit. I think about this relatively often whenever I'm driving and I get rerouted and Maps chooses a different route for me and says it's going to be 8 minutes faster if you go this way. I'm like, okay, I trust you, I guess. But what are the data structures that they have? Well, you have to make sure that you're connected. So can I go from 8 to 3 to 7, and where can I get to from 7? Maybe some other places. I'm trying to see if there's actually a route here anywhere interesting. I guess I can get from 1 to 3, then I can get from 3 to 7, and then maybe from, if I'm at 7, I could get to 8. So it's potentially doing a decent amount of traversals. Or you could have both, too, in both cases, right? Depending on what task if you have enough memory, maybe having both is optimal, too. Let's see here, because maybe you just have a matrix that's kind of up to date or representing something else, like, hey, these are road closures anywhere where there's a 1. So normally there would be a connection, but don't go that way. All right. So something to think about, something you folks might work on someday. All right. And as mentioned, these trade-offs tend to matter at scale. All right, let's see. We're at about 3:30. Do folks want to power through and look at some code and then have the rest of the time to do whatever they want? We're a little bit early. It's going to run a little short. I see some head shakes. Yeah. All right. Let's kind of look at a little bit of code here. See how would we actually represent these. So I'm going to actually show you adjacency matrix first here. Actually, let me do this here. Let's dim the lights. Right. So let's see what this looks like here for adjacency matrix. Now, I told you or mentioned one easy way to do adjacency matrix is just to create a 2x2, or excuse me, a two-dimensional array. Okay, and we've been doing this. Every image that we've looked at has been a two-dimensional array, so we're quite familiar with that. So I wanted to do something just a little bit different. That'll be a little bit more flexible too, and show you more C++ stuff. But how I'm actually going to represent our adjacency matrix here, and you're welcome to look at this code here. Let me sort of mark where we are here. Well, just as good of an array, but maybe something that we want expandable is a vector. So instead, what I've chosen for our representation here is a standard vector of vectors of integers here. Okay, so it's a vector of vectors. So that way I can sort of expand along each dimension. I can get more rows or more columns as I need. Now with an adjacency matrix, these dimensions need to be equal. We need a square matrix, right? The number of rows, how tall we are, needs to be the same as the number of columns that we have. Okay? So that's the idea here. And how to implement this, or something that I don't think we've seen yet, let me scroll up to our constructor, is, well, what's our constructor going to take for adjacency matrix? Well, we need some amount of nodes here. And again, I can say nodes, vertices, right? Because, again, for our adjacency matrix, we need just our total number of nodes, because it's possible that any node could be connected to the other one, right? That's where we get the square matrix from. Okay, so that's sort of my input into this data structure. And then what I'm going to use to start our vector is figure out, well, how many vectors of vectors do we want? And I'm going to use resize here, and just go ahead and size the actual vector to, well, again, how many nodes do we have? So that's going to give us some number of rows here. So we get a bunch of empty vectors of integers at this point. Okay, so then the next step is to fill in our columns and just iterate through each one of those vectors and resize them as well. Okay, so that's the idea. That's the new idea here, something we can do with vector. So let me pause here. Does this make sense for folks? Any questions about resize? All right, cool. Now the nice thing about resize, there's a couple nice properties, and you'll see this in the standard template library, so it's kind of nice to know about. Resize is actually allocating enough space for our vector. Okay, so we've talked about a few times in this class about how vector works, where you push back an element, and then if it's full, right, because behind the scenes it's an array, it'll copy everything into a new array, double in size. It's either double or 1.5 times the size and make a bigger vector, right? But if we just say, hey, resize exactly, to the size that we need, that's pretty fast. Okay, so we're pretty much getting something as fast as an array when we do this. Resize can also take a second argument. It's a default argument right now that'll just also populate. Well, I mean, we might want to know what's actually in these vectors when we resize them. Is it garbage? Is it something else? It'll actually put in zeros for us, which is nice. That's what we want in this representation. But we could go ahead and pass in an argument here and put in like 7 or something, and it'll put in 7s in all of our vectors. Okay. So that's the idea here. All right. Now let's go ahead and run this here, just so I can show you what it does. And this example doesn't need anything fancy. I'm going to compile it with -G though. That's just regular C++. And here, in today's example, you'll find just a little printout here, as shown on the right, of, again, the rows and the columns going across. Okay, and you can see it's just filled in with zeros by default. Okay, and I want to go ahead and just show you resize here. Let's resize and put in 7s or something here, just so you can see that it fills in automatically with whatever the value is. Again, helpful little thing to know, nice optimization in C++. And I'll revisit that idea of this default function argument that you've likely seen in other languages as well, but just a new thing for us to see. All right, so what else do we need as a minimum in our graph representation? Well, we're going to need some way to add an edge. So there's a member function here for figuring out the source, where am I starting from, what's the actual node, and where am I heading, destination. And then here's an exact instance of a default argument. So in C++, you can just say what the type is, the name of this variable, and then you can just set it equal to something. Okay, so you can do this for anything that you create. So for integers, I'm just going to say, hey, by default, the weight is 1 here. Okay, because that seems like a reasonable value if I'm represented a undirected and unweighted graph. Okay. So if there's no direction in the graph, then that means I need to mark source to destination as well as destination to source, right? It's a two-way road. I can get from one node to the other. Okay, does that make sense for folks? Yeah. All right. So let's let me again run that, and then I'll show you what to produce this code here. All right, let's scroll down. I'll show you the print function's not particularly interesting, but I can show it in a moment. All right, so anyways, here's our adjacency matrix. We said 10 nodes, so that gives us 10 by 10 matrix. When I add the edges from 1 to 2, if I look carefully here, let's see. I've got index 1 here and 2, which have been connected here. Okay, and this is 0 indexed here. So if I add an edge from 0 and 4, I should see in 4, and then the column 0, there's a 7, and then on the opposite side, from column 4, going also in the other direction to 0. Okay, there's 7. Okay, so that's it. That can, if you can get your problem in this form, then you can start doing all sorts of interesting traversals. All right. Let's see. Any questions about this code? Representation? Not too bad, right? We tend to use vectors so that you don't trap yourself. You can resize if you need to. Resize will do the copy for you. So if you resize a vector that you already have and make it bigger, it will preserve all the elements. All right, so if I decide, hey, this should actually be 15 by 15, it'll keep and preserve the rest of your graph. Okay. So maybe in some universe, again, I don't know because I don't work at Facebook, but maybe they are just using a vector and resizing as more users join or something periodically. Other little quirk of C++. That I'll highlight on this slide, but here at line 57, you do have to put a space between this arrow, this greater than sign and this greater than sign. Otherwise, it gets a little bit confused. Why? Because it thinks it's like when we do cout, or actually cin, since the arrows are pointing this way. It can't determine if it's the stream in operator. So let me just show you that, because that's going to be one of these things that messes with you a little bit. A template of templates. Let me put it back in here. Okay. Oh, actually this time it did like it. Now in our other example it's going to get confused. I guess it's not ambiguous here. That's good. All right. All right, so that's adjacency matrix. That's one way to represent a graph. Let's go ahead and move forward a little bit here. I think I showed you everything I want here. All right, and we talked about all those things. So now I want to go ahead and show you adjacency list. Okay, and this time for a directed graph. So I'm just going to have nodes. I'm not going to connect them both ways. So again, something you have to think about. Easy enough to design. Now I'll revisit the code in a moment. But I'm going to use a new standard template library data structure. This time it's called unordered map. Okay, so we'll have to look at what that is. All right, so what is unordered map? All right, well this is a new data structure. It's been added since C++ 11. There is something just known as a regular map, which I'll mention at the end of this. But basically what an unordered map is, and you know it by other names in other languages, dictionary in Python, hash table in Java, that's what C++'s version is. Have folks used hash tables, dictionaries? Some folks, yeah, okay. Well, the basic idea, or I should actually say we've been using, and another, the better way to call this is it's an associative array, meaning that we associate some key with some value. Okay, so we have been doing this in our programming, just using an array. Anytime we've been using an array, we have a key, which is the integer, index 0, 1, 2, 3, 4, whatever, and then the value for that key or that input is, well, whatever the type is. Again, usually integers or whatever. Okay? So that's the idea. That's what an unordered map is. We have our keys. Maybe there's strings here, like these folks here. And behind the scenes in C++, there will be a hash function that says, okay, I've got a string here. And for that type, you have a hash function that says, okay, where do I actually store this? What's the actual index? Behind the scenes, everything's still an array, but you have to go through this one extra step of hashing something here, which is basically, again, just saying, how do I take this type here, whatever the key is, and turn it into a unique, ideally a unique index here. Okay, and that's the bucket that it falls into. And then if we look in this bucket, that has the actual value here, which in this case are phone numbers, it looks like. All right, does that make sense, folks? Well, that's unordered map. The data structure is, as it says, unordered, so we don't really have any idea, if I put John Smith or Lisa Smith or Sandra D or whoever, what order the actual keys are going to be in. The data structure is free to arrange these as it likes. So when we iterate through our keys, we're not guaranteed to get any particular order here. If you want an ordered map, that's just simply the map data structure. And that's the difference. Okay? The unordered map has the advantage of, since it is a dictionary data structure, you can access things in the average case in constant time. You look up the key or whatever you're querying for and saying, hey, is John Smith in this database? You pass it through this hash function, and if you get a value back, and that takes roughly constant time, that's what you get with unordered map. A regular map is represented with some sort of tree, and that takes roughly log of n lookup. Okay. So that's the difference. So let's look at this idea of key value pair with unordered map. So here's what it looks like in C++ here. Standard unordered map. Again, since it's part of the standard template library, it's a templated algorithm. The first parameter in the template parameter list, so between the less than and the greater than sign here, is the key, which is an integer, and then the value of what I want to store. This time it's going to be a vector of integers here. Okay, so the key is going to be the vertex, and then the value, the vector of integers, those are my connections. Okay, it's a vector here. We could use a forward list, we could use a regular list, write your own, whatever linked data structure that you want to use here. Again, vector tends to be pretty good. Just have a dynamically resizing array here, but that also works here. All right. All right. So that's our representation, and I'll show you in the code in a moment here. Now, when we're accessing an unordered map, it is actually a pair. So in unordered map, the things between the wicket marks, or the less than and greater than sign here, the template parameter list here, int and standard vector, that's actually a data structure. It's a standard pair, which just consists of, well, pair is two things, so you have the first thing and the second thing. So how you actually access these in C++ is a little bit weird, but you would just say, in this example, key.first or value.second for whatever your key is and your value, okay? Or whatever this, the thing is that's returned from a map. You get the first thing, which is the key, and the second thing is the value. Okay, I'll show it in code, and it'll make a little bit more sense here. All right, so let's actually look at an adjacency list here. I've given probably the most lightweight example that I can think of here. Oops, let me actually move into this directory. Let's split our window. Yeah, let's take a look here. Now this one is, again, as I mentioned, C++ 11, so we do need to compile. Let's go ahead and look at this here. Okay, few things here. Well, let's see here. Let me show you what I did. Now, here's our data structure, which I'm going to highlight here. Now, as I'm highlighting that, the first thing that I did, again, just showing you, we're at the point where I can start showing you some of the odds and ends of C++, is I said, hey, this is really annoying to type out. So, standard unordered map, int, standard vector, int, this whole thing here that I'm highlighting on line 7. So instead, and this is the same as, for folks who have taken C, you can actually use this technique here, type def, and what that's going to do is say, hey, I want to refer to things that are standard order map where the key is an integer and the value is a vector of integers. I just want to refer to that as adjacency list underscore t. Okay, so that's all I have to actually type out to create that type. Okay, so this is something common you'll see, especially in larger code bases. It cleans up the code quite a bit. So if I go ahead and show you at line 33 here I am creating my adjacency list. Okay, so hopefully that makes sense. This is a standard unordered map with keys of integer and a value as a vector of integers. Okay, a little bit of abbreviated, but nicer to pass around in a function or something. Okay, so I just did that here to show you. Now what I want to do is, now that I've got this data structure here, this thing that could represent an adjacency list, I want to add some edges to it. Okay, and in this particular example, I said it was going to be quite minimal. I didn't need to wrap everything into a class. So sometimes you can just have freestanding functions, right? Just regular functions, and use your data structure. I wanted to show you that. It's a little bit cleaner here. So let's look at what it is to add an edge here. And again, I left the long type here, but I could replace this, and I probably should. But when I add an edge, I'm going to take in the graph. I said these are freestanding functions. I'm going to pass it by reference because I actually want to change or add to this unordered map. And then I'll have my source and then my destination. Okay. Okay, so the first part of this, line 14, the graph, or my unordered map here, whenever I want to add something in, I add the key and then, set the value here, okay? So what I'm doing here is I'm saying, okay, the graph, the key, that's the source. In that case, it's a value like 1, 2, 3, whatever. And then I'm saying, okay, push back into that source, okay? Because our value is a vector here, okay? So if this key hasn't been added, unordered map will take care of the details and allocate space for the value, say 1 or 2 or 3 or whatever here. And then when I push back, it'll push back into that vector. If that vector doesn't exist, again, it will create that vector and add in whatever our destination is here. Okay, does that make sense, folks? All right, awesome. Okay, so that's all it takes to add an edge. And again, you can tell this one's directed because I'm just saying source to destination. I'm not reversing it and adding destination to source or anything like that. Okay. All right. So with that said, let me go ahead and run this. Again, you can see that I'm adding a couple edges here. Push this up a little higher for you. Okay, so here I am adding a few edges. 1 to 2, 1 to 3, 1 to 4, 2 to 1, 2 to 4. Okay, let's go ahead and run this. And as I mentioned, we need C++ at least 11 here. All right, compiles and runs here. Okay. And let's see if we can match up. Okay, so you can kind of see the different edges that were added here. Now, what's kind of nice here is I just have my adjacency list here. Okay, it just has the actual connections that are used. Okay, even though there's 4 nodes here, it's not a 4x4 matrix. So this is potentially more sparse here. Okay, so if I have a lot of nodes, now I guess to make this just a little bit more correct, I think maybe I would still add anytime I have a connection that we should see 3 or 4 with no connections. So I guess I could add those as well. But But yeah, that's the idea here. Okay. So we're potentially saving a little bit of memory here, especially if we have a bigger data structure. Okay. That makes sense to folks? All right. Let's see. Let me show you last few things here. Here. Okay. How to print this out. Using some of our tools. Well, if I want to print this out, again, let's see. Starting from here, I'll pass in our adjacency list here. I'm passing it by reference so we don't make a copy. We don't want to change anything because I'm just printing it out, so const. Okay, so we don't want to forget about those things. And then, how do I iterate through an unordered map? Okay, well, I can use a range-based for loop. So starting from line 18 here. And actually, let's make this as big as possible here. A little bit bigger. There we are. And what I'm doing is, grabbing the keys first. Okay. So again, you kind of have to imagine or draw out the data structure. But again, so going down our adjacency list, looking at all the keys, all of our different vertices, and grabbing those first. And that's what I was printing out here. So I say, okay, because really, again, when I'm iterating through an unordered map, it's just a list of pairs. Okay, a pair consists of the first thing and the second thing, the key and the value. So once I've got my key, which I print out here, I say, okay, for all of my things that are in my key here, or the values, so key.second, that's the actual vector, then iterate through those. Okay, and I just use auto to figure out what the type is, value. I might even want to put an ampersand here if this wasn't just a simple integer, maybe, so it avoids a copy, but then that's what's printing out all of my connections. Okay, so that could be something to navigate a little bit with this new data structure. All right, does that make sense for folks? Any questions? So we can represent graphs. We don't need anything fancy. If you do want to, let's see here. If I quit this, and I'll leave this up to you, after class if you want, just to know it's available. But I do have some version of adjacency list here. Let me actually just open it up here. Of using things with, not integers as the key and sort of representing this, with nodes and sort of building it from scratch as well. But so you're welcome to look at that as well. But on an unordered map, this is what it's doing behind the scenes. Alrighty. So with that said, I think we've got a good idea of adjacency list, how to actually put one together. I talked a little about type def. This is a nice little saver for your code. Sometimes it's also just the right thing to do. Because if you're going to change the representation, it's easier to just update the type def, right? They might decide later, hey, those should have been ints, those should have been unsigned ints or something, right? And then you're updating all of your code with just one change, which is nice. So I sort of like that. All right. So with that said, we powered through. Things would end a little bit early here, but we've got all we need for graphs, or we're going to need. So if you'd like, you're welcome to use this time for a few different things. You can either do a little exercise, which will sort of get you ready for homework. It's kind of fun if you take one of these examples and try to represent this in SFML, so drawing the actual circle shape and then the link between them. That's what we're going to be doing for our homework, so you can get ready for that. Otherwise, you are welcome to come talk to me about final projects for this time if you had any concerns. And then, of course, you're also welcome to start your vacation from C++ if you want. And I will not be offended with option number 3. I know we're in Thanksgiving holiday mode. So let me kind of bring the lights back on a little bit. Brace yourselves here. Oops, got a little bit of light. All right. And with that said, I'll go ahead and stop the recording. So if you want to come chat with me, you're welcome to. Otherwise, have a fantastic and safe holiday for those of you who are traveling.